Okay, so in this particular sample problem, it's going to be an application of the Henry's Law. Henry's Law is very useful. Let me write that up on the board here. Henry's Law is useful for determining or describing quantitatively the solubility of gases in liquids. I found a really interesting problem in your book, and I wanted to consider it because it's kind of fun. It's number 49 from chapter 12. It asks us what mass of nitrogen gas is dissolved in an 80-liter home aquarium. It's kind of a fun problem to think about how much nitrogen gas might be in your fish tank if you're one to have fish. And didn't know the answer, so I figured I'd work this problem because it sounds pretty interesting. It's a cool application in chemistry, all right? We can use Henry's Law to help us with this. And it's an application of Henry's Law. And of course, this Henry's Law business is something you're going to want to know for the exam, right? So we got an 80-liter aquarium. We want to know how much nitrogen is dissolved in the water, because gases can dissolve in water. The total pressure, that's the atmospheric pressure above the aquarium, is an atmosphere. And we're supposed to assume that the mole fraction of nitrogen in the air is about 0.78, which is pretty typical, okay? Room temperature, 25 degrees Celsius. That's our temperature. They state this because the Henry's Law constant changes with temperature, so we have to know what temperature to use. The problem says room temperature, and as a chemist and someone who's experienced with these problems, I understand they mean 25 degrees Celsius, or 298 Kelvin. When they say room temperature, that's just what they mean by that, okay? This is kind of vernacular. So if we're going to solve this problem, we're going to start by writing Henry's Law relationship, which again describes the solubility of a gas in a liquid. Henry's Law tells us that if we want to adequately describe or quantitatively describe the solubility in a liquid, we have to multiply the Henry's Law constant for the liquid, Kh, times pressure of the gas. Now, Kh is a characteristic of the gas that we're going to dissolve into the liquid. Okay? It changes. Nitrogen, carbon dioxide, helium, all these different gases have a different value of Kh. You have to find that in a table. It will be given to you on an exam, on the online homework. You should have a table of values. If not, look it up in your textbook. There's an example table in your textbook in chapter 12. But Kh changes for different gases, and it's also temperature dependent. Okay. Now for nitrogen, N2 at 25 degrees Celsius, I can look up my tabular value of Kh. It's in your textbook. Its value is 6.1 times 10 to the minus 4 molar per atmosphere. Again, the Henry's Law value, Kh, depends upon the gas, depends upon the temperature. What that number does for us is it tells us how soluble this gas is per atmosphere of partial pressure above the solution that it's dissolved in. Okay, so this is specific for nitrogen and water at 25 degrees. If we change those conditions, the K also, of course, changes. Now, how do we use this? Well, of course, we're going to plug it into this equation to eventually compute our solubility. Okay, so we're going to write Kh here, 6.1 times 10 to the minus 4 molar per atmosphere. Now I need to multiply that number times P gas. What is P gas? All right. Well, this is the partial pressure of the gas in question. Okay, the solubility is directly proportional to the partial pressure of the gas above the liquid that we're interested in dissolving the gas within. So the details of the problem are essentially going to tell us what that P gas is. Okay? Now you might think it's this number, the 1 atmosphere, but it's not, because we've got air above our aquarium. Now air is made up of multiple gases, not just nitrogen. We're told here the total air pressure is 1 atmosphere. However, the mole fraction of nitrogen is only 0.78. Okay? So it's not pure nitrogen, it's air. Air's got some oxygen, some other trace gases that also exert a partial pressure. But the neat thing, or the easy thing about this, is that because we're given the mole fraction, and because gases are assumed to behave ideally thereby exerting a pressure that's proportional to their mole fraction. We can easily basically multiply these numbers together and decide that the partial pressure of the nitrogen is 0.78 atmospheres as a consequence of this rule of partial pressures of gases. Okay, so there we have it. We've got our two numbers. We just need to multiply them together, and we can get a value for the solubility of our gas in mole per unit liter units. If we work out the computation, we get 0.0004758 mole per liter, because this is in mole units here and the atmospheres cancel, okay? Now, I didn't pay too much attention to sig figs here. I'm just sort of reporting the digit that my calculator gives me, and this would be typical. Usually if we're going to do the rounding to accommodate sig figs, that's done at the end of our problem, okay? So I'm keeping digits right now. But this tells me what the solubility of my nitrogen is in my fish tank, okay? So it's about, what, 0.47 millimole per liter nitrogen dissolved in the water, which is actually pretty interesting. It's more than I might have expected, just sort of from my expectation. Now, we're not done with this problem, because if we read it closely, they're asking for what? The mass of the nitrogen that's dissolved. Okay, so we've now got a concentration, a molarity, but we don't have the mass. So we need to do a little bit more work. But fortunately, we can figure out how to deal with this, because this is my moles per liter of nitrogen, and I've got 80 liters. So I've got to sort of integrate or add up the entire volume of the tank. This would just be 1 liter, but I've got 80, okay? So if I want to figure out how many total moles of nitrogen N2 gas I've got, the first step is to take 80 liters, my volume, and multiply that by my concentration in mole per liter units, such that the liters cancel. Does that make sense? So liters cancel, we're going to be left with mole units. Remember at the tail end of class one day, I told you that there's this equation, the number of moles of dissolved solute is always equal to the molarity times the volume in liters. That equation is very, very useful for problem solving like this. I've used that here. As you can see, the liters cancel, you're just left with moles. That tells us how many moles of nitrogen must be in our entire tank. That equals to 0.03864 moles of nitrogen. Again here, I'm not being overly careful about my sig figs. I'm just writing the value that my calculator gives me. Okay, so integrated over 80 liters, I've got about 38 millimoles, or 0.038 moles of nitrogen. Still not finished, because we're asked for the mass. We've got the moles of nitrogen, but we need the mass in grams, hopefully, okay? So we need to do a moles to mass conversion. Okay, now, fortunately, I think this will be pretty easy for most of y'all, because you've done this in General Chemistry 1. It's a very common skill, very important skill. We're going to go from moles to mass. We do so by using our molar mass or formula weight of our material. Now here we're dealing with nitrogen, N2, it's the diatomic nitrogen. That's got a molecular weight of 2 times 14.01, which is the number that you get from the periodic table, which is of course equal to 28.02 gram per mole. So all I need to do to figure out how many grams I've got is I take the number of moles that I found in the previous step, and I multiply by my conversion factor, which states there's 28.02 grams for every 1 mole of nitrogen. Okay. My mole units cancel, and I'm left with grams. And if I do that computation, I find that my fish tank contains about 1.066 grams of nitrogen. Now in this very last step, if I want to account for sick figs, I have to go all the way back to the beginning where I started to see how many sick figs were present in the numbers that I used. It looks like I had 2 here and 2 here. So my answer should probably also have 2. That was sort of our limiting factor. Okay, we had other more sick figs other places, except for the 80 liters, but we'll assume that it's 80.0. Okay, and I'll report 2 sick figs in my final report, which would be 1.1 grams. So this has been an interesting problem. Turns out that if you have an 80-liter aquarium, a little over 1 gram of gaseous nitrogen is dissolved in the water that's present in that aquarium. So this is an indication that Henry's law allows us to predict the solubility of gases. And of course, that's one of the key learning objectives of Chapter 12. And that's why I've chosen this problem. It's also a little bit interesting just to think about it. I hope you found this useful. See you next time.